Yep, so welcome back to our radiation heat transfer learning journal. The last video we were talking about the heat flux, the scalar version of heat flux, and of course now we want to find divergence of the heat flux, which is like the heat source or heat sink, depending how you look at it, positive or negative, of a control volume. Okay, so we look at a control volume and see how much heat is being absorbed overall or released overall, and the divergence of heat flux tells us that how much is actually being pushed out of the system. So yeah, if I got my signs correct, but anyway, regardless how whether it's a inflow or outflow, net outflow, this is of that control volume. The divergence of heat flux is a very important solution, very important thing, not a solution, quantity for us to know. And yep, and what we need to know to get the divergence of heat flux is this G, or the incident radiation kind of a function. And G, is we've found out before, it's equivalent to over 4 pi, integrating over 4 pi I received. Okay, this is just the physical meaning of it. So you're getting the radiation received over all solid angles. Alright, that was what we have discussed before. I'm not going to go through too much of that, but yes, so we want to get the radiation received, okay, and we want to integrate over all solid angles. So let's integrate from 0 to 2 pi d phi. Okay, so and you integrate from 0 to pi, the polar angle. So this is the azimuthal angle, which is 5, and then we need a sine theta d theta, and this is the polar angle rather than azimuthal angle. So I received will be here. Okay, this is by definition, right? By definition it is this amount. So yeah, now how do we change this? Okay, how do we change this to something suitable that we know? Okay, let's change this. We'll change it to the theta to mu, and we'll get rid of the phi since we have azimuthal symmetry assumptions. So let's write under azimuthal symmetry independent of phi and 1D case. What we'll have is sine theta d theta is actually minus d mu, as we have discussed before, where mu equals to cosine theta. So I'm just going to write d mu here and assume that, you know, all the what do you call it, the variable change has already been known because we've derived it before. Not going to derive it again. And then we have to change this from -1 to 1. Okay, because we swapped around the 0 and pi at cosine theta or mu, or theta equals to 0, mu equals to 1, theta equals to pi, mu equals to -1, but d mu is minus sine theta d theta, and so we swap the limits around and we arrive at this. So what is I received? It is this much, this quantity, and it looks pretty familiar, doesn't it? It looks almost like what the expression for QR actually looks like, except now we don't have a mu d mu, we just have a mu, right? We just have a mu, I mean a d mu at the end. So I can almost just copy and paste this whole expression. Alright, you can copy and paste this whole expression and just take mu out. So I'll just take this mu out. Alright. Yeah, I'll just take that mu out, and we are just left with the following expression. Okay, so yeah, we are just left with this expression, and this is what G is basically like. Alright, if you just copy and paste, and if we take a look at this, it is exactly what I'm talking about. Again, we have 2 pi, and then we have I1 and I2, as mentioned before. Okay, I1 and I2. The physical meaning should kind of be the same, though I wonder why there's a positive here and there's a negative here. But okay, the physical meaning is that, okay, we need the radiation from the top and bottom plates, and we integrate over all 4 solid angles. Okay, so the top plate and the bottom plate are here. Alright, so I didn't change it into all this funny notation here, where we swapped the limits from 0 to -1 to 0 into 0 to 1. I didn't exactly swap the same way. To me, that's not so important as the physical meaning, because that's what you really need to understand the equations anyway. So so this is from the bottom plate, where you have exponential minus tau over mu, and this is from the top plate, where you have tau L in the picture. So exponential minus tau L over mu, and then we have the integral over all solid angles of the source terms, which are this one being from the bottom plate, and that will correspond to this first term over here, and the second one from the bottom, from the top plate going towards the bottom, and that will be this term over here, which is the same as this term over here. And of course, you'll notice that the one divided by mu, the mu by mu, it's actually inside the what do you call that? Yeah, it is inside the it is inside this d mu by mu. So we have from top and bottom plate. So as you can see, there's a mu being if you want to compare with the heat flux, there's a mu in the heat flux there. In this exponential from the top of the plate, there will be a mu there, because this is for heat flux. We actually have this cosine theta in there. That's why we have this extra mu here. Here we do not have the extra mu. We do not multiply the whole thing by cosine theta, so that's why this is missing. We just integrate over all 4 solid angles, and this is basically the expression we end up with. So there's nothing too fancy about this. Again, as you would know, even for G, the analytical solution is left in implicit form, which means you can't quite solve it straight up unless you make further assumptions. So meaning you can't solve this except for making more simplifying assumptions. All right, so that is what G looks like, and since G looks like that, we can just substitute G into the divergence. So divergence is expressed as the following. We will just have everything here pasted here. Alright, so I'll just highlight that. So again, this we have the black body term, which it's over here, and the incident radiation function, which is over here. This whole thing here is G, and that is what your divergence of heat flux actually looks like. Hopefully you know how to derive the equations by now, and you know that it is a very difficult thing just to derive, and it's also difficult to solve using these analytical solutions, which are left in implicit form, because then you have to tell us what the source is, and the source again, it will be dependent on incident radiation from elsewhere, right? If we look at the source term, where is the source term? Yeah, if we look at the source term, it will again be dependent on incident radiation from elsewhere. And of course, you want to, if you have the phase function, it will add another layer of complexity to it, and it'll make it even harder. But whether or not you have this this little term here, you will need to consider incident radiation from other parts of the medium. So it kind of makes it pretty difficult to solve it explicitly, unless of course you can take scattering out so that the albedo is 0, and the only thing you really need to bother about is this. If that is the case, then you don't need to think about G in the source term. Therefore, it becomes more of an explicit relation rather than an implicit relation. Okay, so that's all I have for you this video. Thanks for watching, and yeah, all about these analytical solutions. So the next video we can start looking at cases where numbers actually start making sense. Perhaps we neglect scattering, or we have isotropic. Yeah, or the best case is if we neglect scattering, and we know the temperature profile or whatever. Then we can find out what G is in a more explicit way. But anyway, that is it for the derivation. We can go on to solving cases a little bit later on. So thanks for watching. I'll see you guys again. Bye bye.